All right, good morning. How's everybody today? Happy Wednesday. We've made it halfway through the week, I guess. Sorry for the little bit of a late start. I'm actually hopefully recording the lecture today. And that's in case, sometimes somebody misses class, maybe somebody's sick, they can still watch the lecture after the fact. So I've got two microphones on today. We'll see how that works. One that's hopefully going to my computer and one that's going to the room. So I'm always a little unsure if it's going to work very well. Attendance. It's a good reminder for me. Start that over here. Please initial by your name. We will do another pre-lecture assignment for tomorrow. It's already posted, so make sure you see that. We're going to get into chapter 2, and this pre-lecture focuses on unit conversions, what we also call dimensional analysis. This is kind of the main mathematical calculation and problem-solving approach we're going to use in this course. Okay, there's a lot of things where we're going to go from one unit to a different unit. Okay. And as far as chemistry goes, one place we're going to see that a lot, which I don't know if any of you have had fun with stoichiometry yet. Does anybody know what stoichiometry is? Okay, we've got a couple. You might start with grams of substance, and we might convert all the way to atoms of substance. Okay, so we have to learn how to do these unit conversions. So that's what we'll get into on Thursday a little bit. And don't forget there are homework assignments due on Saturday. So not much new today as far as announcements. I do have if I can get to it. If water is H2O, what's ice? H2O cubed, of course. Chemistry humor. Okay, are there any questions before we get started today? Everybody's in Achieve, everybody's cranking along. Okay, just remember, Achieve is the assignments in Achieve are about 37% of your grade for the semester. So make sure you stay on top of that. I did at least update the latest stuff in the calendar in Blackboard. So hopefully you'll see that, and can help keep you on pace. All right, no questions before we start? Okay, so we left off yesterday. We were still in chapter 1. We had kind of wrapped up with chemical reactions, chemical changes. Okay, so remember, in a chemical reaction, bonds are being broken, new bonds are being formed, new substances are being formed. Okay, so substances with new properties, new structure, that type of thing. Okay, so the identity of the substance is changed. And this was a reaction we looked at yesterday. This is the thermite reaction, highly, highly exothermic. I don't know if they still use it for this, but back in the day, they used to weld railroad tracks back together or weld them together with this reaction. Okay. We talked about that what you're seeing there is actually molten iron. So they would set up this reaction across the two pieces of track, start it off, and it would actually weld those two pieces of metal together. So very exothermic reaction. We'll talk about energy in just a little bit. Physical properties or a physical change does not change the identity. And the common example is a phase change. Okay, even though we go from solid to liquid to gas, that substance is still the same combination of atoms in the same order. Okay, important part of chemistry, and we'll do more with this later in the course. This is just a little bit of introduction to energy. Clearly in a chemical reaction, there are going to be energy changes. Okay? And I've already used the term exothermic to mean a reaction that loses heat. Okay, so it releases energy in the form of heat. We'll also talk about endothermic. Those are the reactions that absorb heat. Okay, so you might have heard those terms before. Okay, the official definition of energy is the ability to do work. That's not so important for us. We're not going to look at the work that's done by the reaction. We're really going to look at just the heat that's released or absorbed. But then, of course, that energy could be used to do work. And you know potential versus kinetic energy. And what we're going to focus on, we're going to focus on both potential and kinetic. The potential we're going to look at is actually, we call it chemical potential energy. Okay, so energy that is stored within the bonds and the arrangement of the atoms. Okay, but potential energy, energy that is stored, versus kinetic energy, the energy of motion. And for us, we're going to talk about our kinetic energy that we're going to focus on is what's called thermal energy. Okay, heat energy. Okay, so we probably don't think about this a lot, but even in a solid, the atoms and molecules are moving. Okay, there is kinetic energy there. It's what we call thermal energy. If we heat up that solid, those particles start moving faster. Okay, so they have more kinetic energy or more thermal energy. Okay, so that's kind of the kinetic energy that we're going to focus on, energy of motion. And here's an example from your book. It involves the kinetic energy of the particles, that energy of motion, that thermal energy. So you don't see too many burners like this anymore, kind of the old school ones. But clearly, as we put electricity into that piece of metal there, it heats up, and the particles in there are going to be moving faster, more kinetic energy. That energy is going to be released to the surroundings and released as heat. And that was supposed to try to show you that the particles were moving. Did everybody see that? Oops, I want to go back. I got to do that again. Come on. Oh, it's not going to do it. But there we go. Oh, wow. There was one of those where I was in my office yesterday looking through the slides, and then it was like, oh, that's actually moving. And it's like, it's kind of fun. Oh, well. Simple pleasures. Okay, so when we do a reaction, okay, we're not going to look as much at physical changes, but clearly if we go from a solid to liquid or gas, we're going to have to put energy in to do that. If we go the opposite way, gas to liquid to solid, energy is going to be released. But we're going to focus mostly on chemical reactions. Generally, reactions are going to go from a higher chemical potential to a lower chemical potential. Those are what we call spontaneous reactions. Okay. We can also talk about going from a less stable substance to a more stable substance. And that's the general direction that we're going to go, just like you would think in terms of a physical example like this. Okay. Mountain bike rider going downhill. It's going to be a lot easier moving from that higher potential energy to a lower potential energy than going the opposite direction. But again, we're going to focus on chemical reactions. And here's one we've had much too much of lately, way too many forest fires. But essentially, as that tree grows, using the sunlight along with water and carbon dioxide to grow that tree, energy is stored. Okay, and then when that combustion process happens, energy is released as we convert to carbon dioxide and water. Okay, So we're going from a higher chemical potential to a lower chemical potential. And here's another physical example. I kind of like this. We use the word stability, so I kind of like that they put the word stable in there. So it's asking, is this high energy or stable? Yeah, that would certainly be high energy. Okay, so we will use terms interchangeably. A lot of times we'll talk about stability. We'll go from a less stable reactants to more stable products. That's typically the way reactions go. But we will also talk about higher chemical potential energy to lower chemical potential energy. That's the spontaneous direction of reactions. A few more examples, just kind of illustrating the high potential energy to low. It's a kind of always good to have physical analogies, thinking about a roller coaster. You know, when you get to the very top of that big hill, okay, you're at the highest potential energy, and a lot of energy is stored for that roller coaster. Same thing with a mousetrap, but again, chemistry, this is going to be our focus, and it's probably a little hard to wrap your minds around it now that it's really similar, going from more of a physical real world example down to the molecular level. Same thing though. Molecules that are less stable, they have a higher potential energy. So see that molecule up there with the 2 carbons and the oxygen? That is, that structure, those bond angles are very strained, okay? That's a very small bond angle for a molecule. So that molecule is highly reactive. And then that energy is going to be released as we form this more stable product. Is there a question? Oh, yeah, theoretically, if those rocks fell and then landed, they would be in a more stable position. Yeah, I mean, they're balanced. I mean, who knows? I mean, with those rocks, how long they might be there, but eventually they are going to, gravity, it's going to bring them down, right? So that would be described as a higher potential energy. And then when those rocks fall, clearly energy will be released in that process as they come to a more stable location, okay? And we see the same thing in reactions, that we're going to go from molecules that are less stable to molecules that are more stable, okay? All right. Cranking along. I've already used these terms. Okay. Exothermic reactions release heat. Okay. And so the common example of an exothermic reaction is a combustion reaction. So you obviously are familiar with combustion reactions. Endothermic reactions absorb heat. Okay, and obviously you'd be familiar with this. We're cooking up some pasta or whatever, and we heat up the water. A lot of energy is stored in that water where those water molecules now have a lot more thermal energy, a lot more kinetic energy, and that energy then is transferred to the food that you're trying to cook. Okay. So endothermic, add heat, exothermic, release heat. All right, and the last thing for this chapter, just because this is where it ends, but remember, science is about experimentation, it's about testing, it's about making observations, it's about figuring things out, okay? So we're going to, maybe formulate a new idea. We're going to make a hypothesis, and then we're going to test it, and then we're going to make observations, and we might revise our hypothesis, and then we keep going in that circular fashion. And you've seen these definitions before. So hypothesis, we make an explanation, hasn't been tested, but we're going to test it. And then we might revise that based on what we observe and what we find out. If a lot of experimental evidence comes together, we might propose a theory. And then we can even go further than that. We can take a theory or a number of theories and come up with an overarching law that explains things. Something maybe like the law of conservation of mass, okay, that you've heard of, where when that was formulated, different theories were put together looking at chemical composition and other things to come up with this overarching law to describe what happens in a chemical reaction. Mass is conserved. Okay, so don't worry about this too much. I'm not going to test you on theories and laws of science, but the laws really explains what happens. Mass is conserved in a chemical reaction. The theories, how or why it happens, they tend to be a little bit more specific, and then the laws tend to be more overarching descriptions. All right. One thing to point out about science is that most of communication, although there are conferences and you go to a conference, you present your findings, if you really want to get your research out, you are going to publish. And these are peer-reviewed publications. And so when you do research in the lab, you write up your research, you send it into a journal, and they will send it out to respected scientists in the field to review it and decide whether it's worthy of publication. They might say no. They might say we'll accept with some revisions, or it might be accepted as is. Okay? But these are peer-reviewed publications to add validity to the research that's going on. And then this last picture, this kind of just wraps up the chapter. Point out a couple of scientists. Everybody see kind of the scary guy up in the top left? Does anybody know who that is? That is Mendeleev, the father of the periodic table. Okay, so we'll be talking about him a little bit. The guy just to his right is Linus Pauling. Probably haven't heard of him maybe, but he won 2 Nobel Prizes, one in chemistry and one in peace. He won the Nobel Peace Prize as well. He was also a huge proponent of high doses of vitamin C, and he would take thousands of milligrams of vitamin C every day. And he did live to 93. So was it the vitamin C? I don't know. And then the next guy on the right, I just wanted to point him out. It was so weird. I'm looking through this book, right? That guy's name is Omar Yagi. I went to grad school with him. And it was just the weirdest thing. I'm flipping through the book and I'm like, I know that guy. So he worked in the lab I was on the 4th floor of the chemistry building at University of Illinois. He was on the 3rd floor. We used to go out to lunch together at times. So he's a good guy. He was at ASU initially. I saw him down there when he was a professor there, and then he is now at UC Berkeley. So definitely moved up in the world. All right. That's chapter 1. Attendance. Good time to take a break. Okay. You probably noticed the number down the side. I'm just going to keep a running total of how many attendances you have. I did not mention this the first day, but maybe you saw it in the syllabus. You do get 3 freebies. You can miss 3 classes without penalty and still get perfect attendance. Okay, I know something happens, you oversleep, car breaks down, who knows what happens. So, if you miss a class, don't worry. As long as you don't miss more than 3, then you'll still end up with perfect attendance for the semester. All right. Before we jump into chapter 2, any questions on chapter 1? Any questions about the course? Everybody's first week going well? Everybody staying healthy? I hope this continues. I have my worries, but we will see. Okay. All right, so let's just crank into chapter 2. You might not find chapter 2 particularly exciting. It's just on measurement, some math, things like that. It's just things we have to do. We have to be able to communicate the precision of our measurements. We have to be able to do calculations with our data. We have to know how to express how many digits we should include in our answer, things like that. And with science, we will, although in this course, we'll probably tend to look more at smaller numbers than larger numbers. But we will look at, particularly in science, you could look at a very large number like this for the distance of the Earth to the sun. And what is that, 149 trillion meters or something like that? And then we have this kind of scary looking creature, this hydrothermal worm. Kind of got to zoom in to see that thing. I'm not sure I want to zoom in to see that thing, but obviously this is quite a small little creature. So that's why we use scientific notation. Obviously, you've scientific notation in the past, but we will use it a lot. So we'll go through it pretty quickly here just to make sure that we know how to write numbers in scientific notation and how to switch between conventional notation and scientific notation. So we will have a coefficient, which is the first part of the number. We will have a multiplier, which is that power of 10 with the exponent. Okay. So you're familiar with that. And then just to highlight, you know what these mean. So 10 to the 0th power is just 1, obviously. And this is going to take a while to go through. I'm just going to click on this really quickly just so we can get those all up on the screen. Okay. So we have our first part of the number, and then we're just multiplying it. 10 to the 3rd is 1,000, 10 to the 2nd is 100. Of course, we can go larger than that. And then if we have a negative exponent, we are multiplying by a smaller number. So I'm going to go through this quick. You guys have had this math before. And this is just highlighting those examples. 10 to the raised to the 0th power is just 1, so we haven't changed the number. 10 to the 1st, we're multiplying by 10, so now we go to 51. We've moved the decimal point 1 power of 10 larger. 2 powers of 10, and then 3 powers of 10. Okay, so just think in powers of 10, and if we have 10 to the 3rd, we're actually multiplying by 1,000, so that number is going to get larger. We can go the other direction. And again, I think for this course, we will tend to be using negative exponents more than positive exponents, because we're going to be talking about, unless we're talking about the number of atoms in a substance, that'll be a large number. But a lot of times, we'll be looking at small dimensions of an atom and things like that. Okay, so why don't we take a little time here before, why don't you write these down? And if you want to talk to your neighbor and work on these, go ahead and write all of these in scientific notation very quickly, and then we'll go through those. guys have masks with you? Do you have masks? All right, let's go through these 4 examples. When I look at these, if I see a large number, okay, so clearly, we see 2.5 million there. Okay, we know that's a large number. Right away, it's like, oh, we have a positive exponent on our power of 10. Okay, because sometimes you'll see, oh, if you move the decimal point to the left, then it's that, it's positive exponent, whatever. I don't even think of it like that. I think, oh, that's just a big number. I know that I'm going to be multiplying by a positive exponent. So we count over 6 places to get, again, the first part of that number we write is a number between 1 and 10. Okay, that's a standard way that we do it. So 2.5 in this case. And so that multiplied by 10 to the 6th. Okay. Next number is even larger. So we know we're going to even have a larger positive exponent. We have to count across, and I'll let the, oh, okay, they're going to write it for me. We'll let the computer count for me. How many do we get there? 11. Okay, hope they're right. Okay. So large numbers, positive exponents, we're multiplying by many powers of 10, that smaller number. Now, when I see a small number, I know that to get that small number, we're going to have to multiply by a very small number, so 10 with a negative exponent. Same thing. Oops. There we go. So count from the decimal point over to creating a number between 1 and 10, and that takes 7 digits, so this will be 10 to the negative 7th. And then the last one, count over 4, 10 to the negative 4th. Okay, so I know that's kind of silly that we're going through this, but just nice to refresh because we will be using scientific notation a lot. We can go the other direction as well. Okay, let's not practice these, but just let's look through this. Obviously, multiplying by 10 to the 5th, that's going to make a large number. Okay, so we're going to move our decimal point 5 places to the right. And so there we go, move it 5 places. Okay. And we end up with 152,800. So again, just try to think anytime positive exponent, that represents a large number. Do the same thing here. We're going to have to move our decimal point 7 places to the right, if it will let me. What did I do? Hit the wrong key. Okay, so move your decimal point 7 places to the right, and we end up with, what, 16,400,000 liters in this case. Okay, now this is going to be a smaller number, negative exponent. So we are now going to essentially divide by 10 to the 5th. We're going to create a smaller number. So we're going to move our decimal point 5 places to the left. And we can keep going. This one, 3 decimal places to the left. And there's our notation. All right, any questions about scientific notation? Everybody's comfortable working in scientific notation? Okay. We're going to look at our calculator in a little bit and make sure we know how to input scientific notation on the calculator, because that's important as well. Okay, now calculations, you have a calculator, so you can just punch these into the calculator. But if we wanted to do this calculation without a calculator, we could, right? So, you know, we could start out, let's actually put parentheses around these. There's our first number in scientific notation and our second, okay? But since all those numbers are multiplied together, there's no order of operations there. So we can rearrange this. Okay, so we can take those numbers and put it together. We could do this. Right? So 3.1 times 2 . 6.2. And 10 to the 4th, which is 10 times 10 times 10 times 10, if we want to really write this out just for fun. Okay? And then 10 to the 2nd is 10 times 10. So now we have 10 written. Now I didn't write in a very straight line, but you get the idea. We have 10 written 6 times. So that's 10 to the 6th. Okay? And you probably know that if you multiply, you add the exponents together. And again, that's as we wrote it out all here, there's 10 powers, or 6 powers of 10. Okay, so we can do that without punching those numbers into our calculator. But since we have calculators, let me see if I can actually get this to work here. Okay, focus. Come on, people, focus. Oh, come on. Oh, there we go. All right, let's zoom in a little bit. Hello, calculator. All right, it's almost visible. Okay, so let's do this calculation just so we make sure to know how to punch in scientific notation. So we're going to do 3.1 times 10 to the 4th. So 3, is that visible? Can you guys see that? I can't see from where I am if I can. Oh, that's not bad, not great, but okay. So 3.1. Now, most calculators, if you're using a TI, there will be an EE key somewhere. Okay? So don't hit the multiplication symbol now and then 10 caret whatever. Okay, I see students doing that all the time. It can work, but there's a better way. There's an easier way. So on this calculator, you will see this EE. It's a second function on this calculator. It'll depend on what calculator you have. If you have a Casio calculator, it'll probably say EXP on it for exponent, but something like that. So we're gonna, on this calculator, since it's a second function, I'm gonna hit second EE, and then an E is gonna pop up, and that's just gonna represent my exponent power of 10, okay, and I'm just gonna put, in this case, 4. So I'm just gonna hit 4, and that's that first number in scientific notation, okay? The nice thing about putting it in that way, it recognizes that as one number, okay? If you do the 3.1 multiplication symbol 10 caret 4, the 3.1 and the 10 to the 4th are seen as two separate numbers. And you can get yourself in trouble if you divide and don't use parentheses and all of that, okay? If you put it in this way, you don't need parentheses because it recognizes that as an individual number. And then we're going to multiply that by what? 2 times 10 to the second. So 2, and then we're going to go EE second equals. Okay, now it wrote my number out in decimal notation. I could sit there and count and put it in scientific notation. If you're not using this calculator, try to figure out on your calculator how to switch to scientific notation. On this one, you will see at the top where it says science engineering is a second function on that very top key. If you hit that, it defaults a lot to what's called floating point, which is decimal point. You can switch over to SCI, which is scientific, and it'll switch you to scientific notation. And so just click enter, and there you go, 6.2 times 10 to the 6th. Okay, now I know a lot of you will have different calculators in this one. It's a good idea to figure out how to switch between decimal notation and scientific notation. You don't want to be on an exam counting decimal points and then maybe messing up your answer. Okay? Any questions on scientific notation? So make sure you find, your EE key or EXP key or whatever your calculator has and use that for scientific notation. Don't use parentheses and 10 caret whatever. Although it can work, but you can get yourself in trouble. Plus, it's harder. All right, let's get through here. We already did this. Go ahead and punch this into your calculator. We could do this manually just by dividing 8.4 by 2 and then 10 to the 7th by 10 to the 3rd. So we'll do that, but just punch this into your calculator to make sure you know how to input scientific notation. All right, so what'd you get for this one? Yes. 10 to the 10th? Did you use your EE key, or did you use, see, you did the old school way. So that's where, you did. Try it again, because you don't need parentheses if you use the E key. So just do 8.4 E7. Okay, and then just divided by 2E3. Okay, so 4.2 times 10 to the what? 4th. Okay, is everybody able to get that? All right, now we could do this. This one is easy enough to do that we could do this without a calculator. We could take 8.4 divided by 2, and we get 4.2. And then since we're dividing, we subtract the exponents. Okay, so 7 minus 3 will give us 10 to the 4th. All right. Were you able to figure out your calculator? Sorry, I don't know your name. Oh. Oh, is it? You got it? Yeah, I don't know. I think it's just because it wants 2 decimal places there for, it'll do an exponent up to 10 to the 99th. So it's just keeping two digits there. But yeah, 04 is just 10 to the 4th. All right. We have about 5 more minutes, so hang with me here. I think we've done enough with this. I don't think we need to do more with scientific notation. So you could go through and practice these. We already went through this, how to input scientific notation. This is a different calculator, again, showing that EE key. All right. Let's get into this for today, just to get past some numbers. So this is actually quite important. And if you're having struggles with your calculator, and if you have a couple of minutes, come down after class, and I'd be happy to help you figure out your calculator. It's really important that you know how to use your calculator. Okay, the last thing you want on an exam is to sit there and struggle punching in calculations and wasting time. Okay, you don't want that. I don't want that for you. You need to know how to use your calculator. And again, we will have lots of numbers in scientific notation, so you have to be comfortable with that. All right, last thing for today. A number without a unit is meaningless. Let me say that again. A number without a unit is meaningless. Okay? So clearly, if we're using a tape measure, our unit is going to be different than our unit for a graduated cylinder. Okay, even if the number is the same. You know, we measure out 40, what is that, about 47 milliliters in this case, say. Say we measure out something that's 47 inches long, but if I just say, 47, that means nothing. Okay, so 47 inches versus 47 milliliters, a unit needs to be there. Okay, obviously we can't communicate our data, our research findings, or whatever if we don't express units. Okay, and here's just showing you some different units. You see even in a nutrition label, you see grams on there. There's others, cups and whatnot. You know, here's some file downloads in megabytes and kilobytes per second and things like that. So we don't have to go through this very much, but just first realize, gotta write a unit. You're in the lab, you're doing an experiment, make sure a unit is there with your number. What are common units that we will use? We will avoid using English units in here. Scientists don't do that for lots of reasons. One, the English system of units really doesn't make sense. The metric system is the way to go. Everything's powers of 10. It's all good. We will do some conversions just because you will still see English units and you should know how to convert. But we will focus mostly on the metric system, length in meters. Mass, we'll probably use grams more than kilograms, but the SI unit of mass, System International, that scientists have agreed to use, kilogram is actually defined as the SI unit of mass. Volume unit in liters. You've seen those before. Here's a few more. Kelvin should actually have a capital K after Lord Kelvin. But you'll see it in this lowercase k, but it should be a capital K. We will use Kelvin and Celsius for temperature. We will not use Fahrenheit. I will show you how to convert just because you will still see Fahrenheit out there, but we don't use that in science. Yes. Yeah, so the metric conversions I expect you to know, and we'll go through those. We'll probably do that tomorrow, okay? But like any conversion from like an English unit to a metric unit, I would give you those, okay? Are we out of time? Oh, I have one more minute on my watch. Let me, last thing for today, just because I got to get this in. The mole. Okay, not that little blind creature that burrows underground, not that kind of mole. The mole is going to be very important to us because it is the unit for amount of substance. Okay, and I know it seems kind of scary, but atoms are really, really tiny. Okay, so to get to when we start talking about an amount of carbon or an amount of oxygen that is something that we're going to work with, we need lots of atoms to get to, for example, 12 grams of carbon. And I throw that out because that's the standard of where the mole is defined. So how many atoms are in 12 grams of carbon? You know this. It's a special number. Come on. Yes. Avogadro's number. So the mole, thank you very much. 1 mole is 6, it's right around 6. We usually carry more significant digits, 6.022 times 10 to the 23rd. Okay, now we need a unit there. It might be atoms, it might be molecules, it might be ions, charged species. So a lot of times we will just say particles. But just to kind of give you a feel on your way out the door, okay? To get to 12 grams of carbon, 12 grams, that's not even half an ounce of carbon if we want to go to the English unit. Half an ounce of carbon. That's how many atoms of carbon we need. 6 times 10 to the 23rd. Okay? So think about that on your way out. And then I'll tell you a joke on your way out the door as well. Okay? So a neutron. Neutron goes into a bar. Says to the bartender, how much for a beer? The bartender says, for you, no charge. Neutron, no charge. All right. If you have calculator questions or other questions, please come on down. All right, take care.